In this screencast, I'm going to explain why this theorem in Anton section 12.6 is true. It decomposes the acceleration into two components, one parallel to the velocity, one component in the direction of the normal vector. All right, to do that, we're going to need to talk about one result that's going to help us derive the second half of it, which is the harder half. Okay, so let's start to get to that now. So we're going to assume we've got a smooth curve. That means that the derivative vector is non-zero. Okay, and we know that we have our arc length formula, which gives us a relationship between our parameter s and t, integrating from some number up to t of the length of the first derivative. That shows that s is a function of t. Now, by the second fundamental theorem of calculus, we know that the derivative of this function is actually just equal to the integrand evaluated at the upper endpoint. Now that's a length, and we're assuming that derivative vector is never zero, so that's always got to be positive, and therefore we know from Calc 1, if your derivative is positive, you've got an increasing function. If you have an increasing function, it's a one-to-one function, and that means it's an invertible function. So what does that mean for us? That means we can theoretically, at least, solve for s in terms of t up in this formula. All right. That's a possibility. We've seen that in our homework. We usually compute this integral on the right-hand side, and after we do that, it gives a relationship between s and t. That's not always going to be very simple for us to do. Might even be impossible for us to do sometimes, but at least theoretically, we can solve this equation for t in terms of s. And that's going to give us that t is going to be a function of s. All right, now what we're going to do next is look at the unit tangent vector to the curve. All right, so just writing this to emphasize that t is a function of s. Looking at capital T, which always represents for us a vector, and it's the unit tangent vector to the curve, we're going to express that in terms of s and then compute its derivative. Again, this result that we're going through initially is going to be needed to look at decomposing the acceleration in terms of the normal component of the acceleration. So now what we're going to do is, instead of just writing t, which is a function of s, or t of s, we're just going to say t is a function of s and write it in this fashion. Now, if we want to compute the derivative of the tangent vector with respect to the variable t, we can do that. That's equivalent to computing the derivative of the unit tangent vector when you're thinking about that as a function of s. To do that, you're going to use the chain rule. You're going to take the derivative of the outside function like normal and multiply that by the derivative of the inside function. Now this is a vector quantity, this is a scalar quantity, and we usually write our scalars in front of our vectors, so we're going to do that. Put ds dt and then times the derivative of the unit tangent with respect to s. All right, and that can show us that the length of the derivative of our tangent vector with respect to t is equal to the speed, or the magnitude of the speed, times the length of this vector, and that's how we define curvature before. Okay, so just skipping ahead a little bit, we can see that we get the length of the unit tangent in terms of, or the derivative of the unit tangent in terms of the curvature, and the speed, or the magnitude of the speed. All right, now we know from before that the velocity vector is just the first derivative of your vector value function. Now we can rewrite that by multiplying and dividing by the same quantity. It's like multiplying by a convenient form of 1, and that normalizes this vector. If you take a vector and divide it by its length, that's a unit vector. This is just the speed of your curve, and we're going to write that ds dt. Okay, that's from our arc length formula. This is a unit vector, and since we know r prime is a tangent vector, it's got to be equal to the unit tangent. All right, so that's the first half of the derivation. Okay, that's the first half of the theorem. Looking back into the textbook, that's all we're doing, just rewriting the velocity as a scalar multiple of the unit tangent vector. That's not very surprising. What's more difficult to verify is the second portion, that the acceleration you can decompose in terms of the unit tangent vector and the unit normal vector. All right, so we'll do that now. So we're going to differentiate the velocity function with respect to t. That's a vector derivative. Doing that is equivalent to differentiating what we just computed, the speed times the unit tangent vector. To compute this derivative, we got to use the product rule. So it's going to be the derivative of the first function with respect to t that gives us the second derivative of s times the second one left alone plus the speed, the first function we're leaving alone, and we're multiplying that by the derivative of the second function. Now, here's where we're going to use our result from before. We derived initially that this is equal to ds dt times dt ds, so it's our speed times our unit tangent vector, the derivative of it with respect to s. This vector we know is parallel to the unit normal vector, so if we normalize it, that is divided by its length, then we'll have the normal vector itself. We can't just divide it by its length. We've got to multiply and divide by its length, so it's like we're multiplying by 1. The first term's left is unchanged. Now we're going to multiply by that length and then divide this vector by that length. All right, we're also combining these two terms together, so we get ds dt squared. Okay. Now this vector here is a unit vector, and we've seen from our classes before that that vector is parallel to the normal. So it must, in fact, be the unit normal vector. All right, so rewriting this all, we've got the acceleration, what we started with, is equal to the second derivative of the position function of the arc length function with respect to t times the unit tangent vector plus a scalar multiple of the unit normal vector. And it's the square of the speed times the curvature. And we're just going to define this to be the tangential component of the acceleration, the scalar part of that, and this is the normal component of the acceleration, and that's the scalar portion to go with it. And that's the verification of the theorem you're going to see in your textbook. All right, and they're going to use that notation, a sub t and a sub n, to represent the scalar components of acceleration in the tangential direction and the normal direction.